since we introduced the normal distribution back in section 5, all the lectures that we've done since then have sort of been leading to this one, because what I've been trying to show you is that the normal distribution, and when I say normal distribution, let's throw the t-distribution in there too, because it's really just a normal for small n's. Right? The normal distribution and this idea of basing our methods off of a distribution gives us a flexibility that we can exploit mathematically. So if I can teach you what a distribution is and the shape of it and how it captures the area, and area is also percentages and probability, then if we reconceptualize what the distribution represents, we can do more with it. So we're doing that again today. Right? And we're sort of building off of this idea of comparing our samples to something else. So in chapter 7, we compared our sample to an actual, but we don't know the answer, population mean, right? X bar to mu. What I want to do today is I want to compare two groups within our sample to what we would expect to see in the population. So what we're going to look at today is finally introducing like a dependent variable into this. So let's explain how we're going to do this. Coastal, like many college campuses, has a parking tradition. And what's the tradition for parking at Coastal? There is none. It's awful, right? Every student that buys a parking sticker believes that that sticker should entitle them to a spot. But parking doesn't work that way. So if you sell 2,000 stickers, that does not mean that you should be guaranteed a spot, because it flows and ebbs and parking sucks. This is not unique to Coastal. When I was a graduate student at Michigan State, we had the same issue. You could actually pay for a parking sticker, park 2 miles outside of campus, and then you paid for a bus pass, and you could take the bus from your parking spot to campus. I don't think that would fly here at Coastal, but we're getting close to that. The one on 544? Yeah, that one. Okay, park there, take the shuttle in. All right. So let's do this example. Have you ever walked to your car and felt like somebody wanted to murder you because they were stalking you? You've had that experience. I have actually stopped and offered people a ride to their car when I was at State. I'd park at the sort of pedestrian entrance, and I'd sit and I'd have my window down, and if somebody not too scary looking would walk by, I'd say, hey, you want to ride? I'll take you to your car. In hindsight, that might have been a little aggressive, but it was a friendly aggressive. So let's call those people intruders. Because what do they want? They want to come into your parking spot. Then you have those times where you walk to your car and it's like peaceful and quiet. Nobody's going to run you over. There's no intruder. Question is, do you behave differently when there's an intruder versus when there's no intruder? Now let's think of the ways in which you could behave differently. Somebody wants your parking spot. You're walking to your car. How can you behave differently?
Take it for the agent.
Well, it's your spot. Your car's there. You're leaving it. Sorry. You rush. Okay. Why? Okay, so there's a little bit of pressure here, like, I want that thing you're done with, hurry up and get out of it. That's you. How would I react? I might take my time, because after all, it's my spot. There's plenty of, well, there aren't plenty of spots. There are other places you could, look at other than looking at me. So I get in my car, I buckle up, adjust all the mirrors, make sure the air con and the radio station are set. Okay. Then you start the car. You want to look a few times because you don't want to run over a pedestrian. Right? want to look around, be safe, and maybe I need to respond to an email on my phone before I leave, or get on my Harry Potter game, get some more spell energy for John, just whatever I need to do. Yeah. Some of you were thinking, yeah, that's a thing. It's not so bad. And then I'll leave when it's, time and appropriate, and all conditions are safe. Okay. So we have two possible outcomes. We could hurry up, or we could slow down, or what's the third option? No, it couldn't matter at all, right? Because, we're just talking about getting in your car and leaving. Most often when you're trying to leave, you're actually intending to go someplace else. So when I leave here, don't get in between me and my car when I leave here about 3:50, because I'm going to get my kids. And so if you want to come talk to me, you're going to have to talk to me as we go to my car. And the conversation is going to end when I get in my car, because I'm leaving. It's a happy time. So let's see what happens. An actual study. This is real social science here, folks. 15 drivers in each condition. So we can look out the window. We can watch this happen. Collect data. How long does it take for a person, once they get in their car, to leave their spot? 15 observations for the intruder. So somebody is there, sort of lurking. Car's crept up. It took, on average, that's X bar 1, so group 1 is the intruders, 40 seconds. Let's call it 41. 41 seconds, get in your car, start it, vacate the spot. That 15 observation group has a standard deviation, that's S1, of 10.42 seconds. So that's the average distance from the mean. And S sub X bar 1, that's the standard error. So that's taking into account the sample size. That's why we have the divided by n, square root of n1. Okay. These are all things we've calculated before. We'd call these descriptive statistics. The no intruder, different 15 people in their cars. That average was 31.67 seconds. Let's call it 32 seconds. Is that different from group 1? Yes, the two samples are different. So, untrained person that has not taken this class before, is there a difference when somebody is trying to get your parking spot? Yeah. Trained person taking this class, is there a difference when somebody tries to get your parking spot? Maybe. Problem is, this is just a sample. We need to see how likely it is that you would get this difference of 9 seconds if in the population there actually is no difference. No, stupid. Okay. So what we have done before, like in chapter 7, we had a sample mean, and then we tried to sort of evaluate how likely it is we would get that sample mean from the population mean. Even when we first introduced this, right, when we were talking about your test score on a standardized exam, how likely is it that you would get that score given the distribution of all the scores? I think that's like chapter 5. And that's called the percentile. Now what we're going to do is we're going to look at what is the probability of two sample means from a distribution of differences between sample means. So we're going to take our normal distribution and we're just going to give it a new name. And it's going to be the sampling distribution of the difference. Still the same shape, still the same tables, T and Z, depending upon your sample size. New name. The sampling distribution of the difference. It's the distribution of all possible differences between two groups. So before, when we were talking about a standard normal distribution, where is it centered? The mean in the middle, called mu. Mu, right? All we're doing with this distribution is saying it's still a distribution, but now it's the distribution of the difference between two groups, mu1 and mu2. Remember, thinking back to my magical upside down bucket where you reach in and you grab some candy or whatever that example was, right? You all are going to get different samples. So if you repeat this driver study, you would probably get different results. Now, when I say results, I mean you get different descriptive statistics, right? So you look at 10 in this parking lot over here. Like, would we expect there to be different behaviors in different parking lots? Is there a dangerous parking lot on campus? The ones where, like, you don't mess around with people because... Which one?
I don't know what that one's called. Closest one, 501.
GG lot?
Yes.
Yeah. People are a little intense there? They're like, I'm out of here. Boom. Okay. Yeah. I bet life would be a little different in our whatever lot this number is here. Well, YY is always empty. I never see cars in that lot. I don't actually believe people park in that lot. But this one here, this one's a little calmer because it's gated. A little bit more exclusive. You know, we get, although it means we're faculty and we're old and slow, so that might be why there's a difference. Okay. So if each of you do this, you're not expected to find a 9-second difference, right? We believe that the differences themselves are distributed. Okay. Focus on this last point there. Although we expect there to be no difference, what is that thing that we have that we really state that we don't believe there's a difference? And that's sort of our basis in social science from where we start from. It's the null hypothesis, right? The null hypothesis, the thing we're testing, is that in fact there is no difference between these two groups. We expect there to be no difference between the two groups. So mu1, whichever it is, and mu2, there should be no difference. Okay, the grouping. What is 1 and 2? That's your independent variable. That's your treatment. That is your cause. What mu is measuring, that's your dependent variable. So you're measuring it in terms of time. Time to leave the parking spot. That's your dependent variable. First time all semester, I'm actually teaching you statistics where we're going to incorporate both an independent and a dependent variable. This is why this is important for your papers, because this is the stuff you really need to do. What does this sampling distribution of the difference look like? It looks like all the other ones that we've already done. The mean is 0, because mu1 minus mu2 is expected to be 0. In terms of symmetry, it's approximately normal, which means that the sample size matters, and you could shift between using a t-score and a z-score. The shape is determined by the sample size. Because when the sample size is smaller, the tails get a little thicker. They lift up a little bit. That's why we use the t-distribution. Because the sample size matters, our measure of variability is still going to be a standard error. But this one looks a little different. This one's a little different. So this is the standard error of two groups. And when I go back to this screen, right, here's our two groups. Here's x1 and x2. We're going to have to compute a standard error that reflects that we're actually drawing from two different samples that have different variances. So that'll get interesting in a little bit. So let's test this theory. Okay, let's test the theory of an intruder changes your behavior when you're parking. First step, the null and alternative hypothesis. The null hypothesis, the thing that we're actually testing, is that the time for the intruder is the same as the time for no intruder. Another way to state this, the mu of intruder minus the mu of no intruder equals 0. This is the null hypothesis. This is where we start from. Our alternative hypothesis, the one that we're looking for evidence to support, is that the mean of the intruder group and the mean of the no intruder group are not equal. So the difference exists because of the two groups. If we wanted to get really particular, we could actually test directional hypotheses. And we could say mu I minus mu no I is greater than 0 or less than 0. So if the difference is greater than 0, that means the intruder group takes longer than the no intruder group, which means you're like me and you take your sweet ass time. If it's less than 0, then you're like her and you're trying to be nice. Strangers. For no good reason. These things exist, but generally speaking, we just stick to the, is this different? Especially in intro stats. So the next step in our scientific method is to make a decision about the null hypothesis, because we've got some data. How do we make the decision about the null hypothesis? Well, we're going to calculate a test statistic. And we're going to follow this process here. First step, calculate the degrees of freedom. So we're going to evaluate how big our sample is. With this, because we have two groups, right? We have two samples, the intruder and the no intruder group. We actually have to combine the degrees of freedom for the two groups. Now, we've calculated statistics, like the mean of those two groups. So we've used up a degree of freedom. So our degrees of freedom are going to be the number in group 1 minus 1 for that group, plus the number in group 2 minus 1 for that group. Outside of intro to stats, we'd say that the degrees of freedom is n minus k, where k equals the number of groups. And in fact, I think we'll see this when we get to chi-squares, and you can have multiple numbers of groups. So we have 28 degrees of freedom. That leads me to believe we're going to use the t-table, because t's right at that sort of edge. Looking at my t-table, next step is to just decide which column it will contain the critical values. I'm going to use the standard middle column because I'm going to say I'm going to put 5%. I'm going to put 2.5% in each tail for my region of rejection. So with 28 degrees of freedom, the critical value of T is 2.048. 2.048. These are going to be my boundaries. Gives me 95% in the middle. If we find that the difference lands in the region of rejection, what we're saying is that it's a very low probability that we would have observed a 9-second difference when in fact there was no difference. So if the null hypothesis holds, it would be less than a 5% chance that we would have gotten a sample difference of 9 seconds. So how do we calculate this? We're going to change our t-test a little bit. This is called the t-test for independent means. So the idea that the reason, yeah, let's just go with this. All right. Take a look at this equation. T equals the sample mean difference divided by the standard error. How is this different than our other ways of calculating t and z scores? What's sort of missing from this? If you had to sort of go back to our how we initially calculated a z-score, what's different about this one? What Greek letter you would expect to see is not there? Nope. That's this. It's not that one. It must be the one up top. What would you expect to see? So what's mu's not there, right? So we have our sample mean, right? We have our x bar. Where's mu? Because these t and z scores are usually observed minus expected divided by your variance. So I've got observed, the observed gap, minus nothing divided by the variance. Why don't we put the mu's up there? Well, not knowing has never really stopped us before. So why doesn't it look like this? So we don't know what mu1 minus mu2 is, right? But we have an idea, don't we? What's our idea of the difference between mu1 and mu2? It's what?
Roughly 0.
It is 0, right? According to what? According to the null hypothesis. So that's why we're not going to try to confuse you by putting this in here, because we expect it to be 0. So let's do some math. The top part of the t-test for independent means is just the difference between the two sample means. So 41 minus 32. We got that one. The denominator, that's our measure of our standard error. The standard error that's computed between two different samples. Okay? So this is how we do it. And it looks a little gnarly. It's not that bad. It just looks gnarly because we're combining superscripts and subscripts really close to one another. So for example, this top part here, S1 squared. All we're doing is taking the standard deviation of group 1 and turning it back into a variance by squaring it. Divided by N1, which is the number of observations in group 1, which is 15. So S1 squared divided by N1, that's just this first part here. Go through, do the math, we get a standard error of the difference of 3.74. Okay. Calculate t the same way, the difference minus or divided by the variance, which is now our standard error. The gap is 9 seconds divided by 3.74, which gives me a t-score of 2.42. Am I happy? Yes. Why? Because my 2.42 is in the region of rejection. How do I know that? Because it was 2.048. So I'm going to reject the null hypothesis. I'm going to say that from the evidence in my sample, I reject the null hypothesis that there is no difference in the amount of time it takes to leave a parking spot when you have an intruder versus when you don't have an intruder. 9 seconds is a big enough difference in my sample for me to say there probably is a difference. All right, here we are in the region of rejection. That's all I care about is it statistically significant or not? The book tells you you can look at varying degrees of significance, but again, light switch for us. It's either on or it's off. We either reject the null hypothesis or we fail to reject the null hypothesis this time with this sample. The mean departure time for the 15 drivers in the intruder group is statistically significantly greater than the mean departure time for the 15 drivers in the no intruder group. So people are probably like me. Why? Present series of studies is consistent with prior findings that people display territorial defense in public territories. What is new about the present research is that it suggests people sometimes display territorial behavior merely to keep others from possessing the space, even when it no longer has value to them. So you all are examples of people who display territorial behavior in a public space. In fact, most professors rely on it because you sit in your seat every time. Like, this is my seat. And you walk into a class and somebody is sitting in your seat, you don't know what to do. And you're like, hey, that's my seat. What are you doing here? I witness it almost every day. This takes it to the next level by saying, it's the end of class. You're done. Somebody sort of walked in, and because the next class, they don't really wait for us. I don't know if you've noticed that, but. Yeah, they're like ready to come in at a minute before class is over. And so, at least that's how I feel, right? I'm up here, I got my stuff. In walks John, and John's like, hey, Frederick, how you doing today? It's like, still my time, still my spot. Like, you're breaking the unwritten rule of bothering me. Don't do that. So this happens all the time. I'm sure you can think of other examples where you're slightly petty. My favorite this summer was we bought a new couch for the new house, and immediately both the cat and the daughter claimed the same spot on the couch. They still go at it for, like, she'll get up to go somewhere, the cat will jump in it. I'll ask her to do something. She's like, if I do, Daisy will take my spot. It's like, it's a cat. You can just, like, shoo it. Nope. Let's do one more example. This time we're going to have the two groups be different sizes, which we can do. It was just coincidence that before it was 15 and 15. Let's do different sizes, because sometimes it might be harder to observe the treatment condition. This is the effects of a healthy living and exercise intervention on kindergarten and first grade students. And let's measure their ability to jump rope for 30 seconds. I have one of these creatures. I don't think he could jump rope at all, much less for 30 seconds, but maybe if he took a class that would teach him how to jump rope, he would do better. So we have a treatment group, and then we have a control group. Just average kids, regular kids that have not received the treatment. The two group sizes are different, 16 and 11, so we'll have to pay attention to that. The treatment group, 27 jumps in 30 seconds, which is probably more than I could do. The control group, let's be nice and call it 12. I think there's a gap between 27 and 12. State the null and alternative hypothesis. Well, the null hypothesis is that there's no difference between the two groups, that the treatment had no effect and kids just jump rope to jump rope. You don't, it's just, they don't need to be taught that. The alternative hypothesis is that the two means are different, and therefore there is a difference between receiving an intervention and being taught how to do something and never being taught. So again, the expectations for the null hypothesis is that the mean of the intervention group and the mean of the control group, there's no difference. See? No difference. First step, calculate the degrees of freedom. Our two groups. Group 1 had 16 students, Group 2 had 11. That gives us 25 degrees of freedom. We need the 25 degrees of freedom to figure out what the appropriate critical value is. 25 is still under 30, still on our t-table. 2.060 according to the middle column. So that's going to be our critical value, 2.060. If it's greater than 2.060, then we are saying that it is a very low probability, less than 5%, that you would observe this difference in the sample when there is no difference in the population. We're going to do a t-test. It's going to be the same procedure. We're going to look at the difference between the two sample means and divide it by the standard error of the difference. Okay, so that thing I told you about the standard error of the difference. Remember how sample size is really important? Well, it was convenient for us to have two equal-sized groups. When you don't have two equal-sized groups, then you have a disproportionate amount in each group, and it gets a little funkier to calculate the standard error. And when I say funkier, I mean it takes 2 slides instead of 1. Nothing here that's too scary. There's no new operators or functions or, I don't have to teach you another Greek letter. You just have to plug in the things that we know. So we know what N1 is. N1 is 16. It's the number of people in the first group. 16 minus 1 times, there's that S1, which is the standard deviation squared. So we're just turning it back into a variance. So we'll do that first. We'll do the parentheses first, then the multiplication. Plus the same thing for the other group. Divided by N1 plus N2. That's the total N minus 2. There's our 2 degrees of freedom being taken out. Then we'll multiply that by a number that's meant to sort of balance how much difference there is between the two groups. So we'll just sort of go through and do all that. I'll wait for the slide copiers. Yes. Yes, I will give you an equation sheet. Yeah. No statistician that works and does this for a living does it without notes. Anytime I need to do something, I grab a book and I look it up just to make sure. That's useless. Yeah, you shouldn't have to memorize them. I show them to you, and I think you have sort of an understanding of what's going on here, right? You have two groups of unequal sizes. So you need to take that into account, the fact that one is 16 and one is 11. So we're going to do that by putting in the sample sizes a bunch of times as a way to sort of distribute the variance appropriately to the two sizes. So as long as you know that, hey, I have to calculate the standard error, then you will go to the equation sheet and be like, oh, this is how you do it. I haven't even memorized this. I know it's complicated, and I know that, hey, I better look this up. So if you come to my office for extra help, I don't do all this stuff off the top of my head. Some of this, like this, calculating a test statistic is usually the difference between what you observe versus what you expect divided by some measure of variance. That's the same every time. I just have to know, okay, in this situation, my variance is the standard error instead of the standard deviation, because I'm dealing with samples and sample sizes, so I need to divide by the square root n. You just sort of pick that up. So I give you a 2-page equation sheet for the final exam, but you have to know which equation to use. So the second slide later, the answer through all of that is 3.88. How would you even memorize that? I don't understand. Okay. Well, you didn't, because that's why you're here. He said that, not me. I'm not being mean. So we get a standard error of the difference to be 3.88. 15 jumps difference divided by our standard error gives us a t-score of 3.97. That's really more than 2. I'm happy. Because now I can show in my data that it's very unlikely that we would have observed a 15.5 jump gap between the two groups if the training had no effect. Right? Less than a 5% probability that you would have that. In fact, and this is why I think Howard does this, where he goes through and he, does the different levels. Like 4, this is really out there. It's not just a less than 5% chance. It's less than a 1% chance that you would just have mistakenly grabbed the wrong sample from a distribution that had no difference. Yeah. By the way, when I do this on the computer gives me the actual percentage. It's called a p-value. It's a probability value. It'll tell me exactly what the probability is. So it'll be like p 0.0002. So you might see that. If you're reading an article in another class, and that's what the p-value is. It's the actual probability of observing that sample if the null hypothesis were true. So our conclusion is the average number of rope jumps in 30 seconds is statistically significantly greater for the 16 students who received the intervention than for the 11 students in the control group who did not receive the intervention. Why? This finding suggests that programs emphasizing the enhancement of basic motor skills that children apply in a variety of games and sports may be an effective approach to increasing overall activity and fitness levels of young children. So if you want to teach them how to be active, you should teach them fundamental things like how to jump, squat, run, start, stop. So that's why when you have kids that are so little, you play games like red light, green light. So run for a while and then stop yourself from running. Because not walking into things is a fundamental skill that you should have. And in fact, the better you get at being able to start and stop, the better you get at sports. Like imagine a running back in a football game being able to turn very quickly. That might be a useful skill to avoid being tackled. Or a basketball player that once they get going, they can slow themselves down so they don't like just run off the court and off into the crowd. So they're saying if you're going to teach kids how to be physically active, you start with the simple things, like jumping up and down without killing yourselves. And trust me, as a parent of a small child that frequently does things that I don't understand, I understand this, right? You have to teach your kids how to like sit down and stay sitting, because that's an important skill you'll need later in life, like right now. We can adapt this for different situations. So what we've done now, or what we've done, the first two examples were different populations. So they were different cars or different students. But what if it's the same student? What if we want to give them a pretest and then give them the treatment and then give them a post-test? We can do that. That's known as, so what we've done before is between subjects where you only participate in one group. We're going to do within subjects, so within one person. Not between two groups, but within one person. Like I said, the pretest post-test design is probably the most familiar that you'll have with something. You might even do this in some of your classes. You come in on the first day, you take an exam, even before you've even taken the course. And then at the end of the course, you take another exam. And what we're doing is just seeing if you learned anything in the course. It's called assessment. Probably should do that in here sometime. See if anybody actually learns anything. There's another form of statistics known as time series. This is much more common in economics, where you have repeated measures over time. Like third quarter increase in GDP was 1.9% the last quarter. Well, if you're an economist and you're studying economic growth, you're going to have a chain of those measurements across time. That's known as time series, or sometimes we engage in what are known as longitudinal studies. Yeah, that longitude, longitudinal. I actually was a participant in a longitudinal study when I was a college student. I got interviewed like every 2 years after I left high school. Never went back and saw what it was about, but they asked me questions about school and I don't know. But it was nice because I got like $100 every time I did it. You have to encourage people to stay in the study, because if I go away and I don't participate, then their data is incomplete. So try to get into those ones. So here's a pre-test, post-test example. 20 parents. Instead of experimenting on the children, let's experiment on the parents. 20 parents tested on their knowledge of childhood depression and anxiety. Do little kids have mental health issues that you traditionally ascribe to adults? 3 weeks later, following a web-based program, the same parents were retested on their knowledge. So give them a pretest, have them take a webinar, and then at the conclusion, test them again. Not immediately after the webinar, but give them some time. So this data is going to look a little bit different. So our pretest is when I took the test the first time. So let's say I took the test the first time and I got a 12. I'm the subject. I take the course, I learn a lot, I think highly of myself, I'm going to give myself a 29 on the post-test. So me at time 1 was a 12. The other 19 parents that took it, our group at the first time, had an average score of 15. I'm going to count that as questions right and not as a percentage. 15 questions right. We took the web-based course. 3 weeks later, we took the post-test. I got a 29. My group of the same parents from the first group, but just later, we all got a 21 on average. Is that different? Is 21 different than 15? Yes. And if you didn't have this class, you would say, well, yeah, look, the scores went up. But again, remember, we're just a sample. We're just one draw from that infinite distribution. We have to see how likely it is that you would observe a difference of 5.5 questions, 6.5, no, 5.5 questions when the training had no effect. So our data is a little bit different this time. The data is paired. So we're going to have time 1 and time 2. And we're going to have different scores. Because our data is shaped a little bit differently, we're going to introduce a new sort of version of math. D stands for delta. Delta stands for difference. So if we were to calculate the delta, it would be plus 17, plus 10. Abby's pretty smart, plus 29. John, we love John. John lost 1 point. And then we can do the average of those numbers, right? Sum divided by 4. That's essentially what we're doing here. So we can sum the differences. That's the sigma of d divided by n d, the number of differences, which is the number in your sample that have both scores. That's really important. You got to have both scores. If you don't have both scores, then you're missing data, and we can't include you in the sample because we don't have anything to evaluate. So the average of the difference scores, again, going through all, what was it, however many parents there were, 20 parents? So the average difference was 5.6. Calculate a standard deviation. It's the sum of the differences. So the d for each observation is the individual level difference from the mean. So really, all we're doing is replacing x with d. We'll click calculate a standard deviation of the difference. There's 4.3. So now we have our measure of central tendency and our measure of variance. So we know what our sample looks like. The null hypothesis is that the average difference would be 0. The alternative hypothesis is that the average difference is not 0, because we should have observed some change between the two times within the groups. Degrees of freedom, n minus 1. Again, we have one difference. We've calculated one sample mean. If our degrees of freedom is 19, we want to put 5% in the two tails. 19 degrees of freedom. Middle column, 2.093 is going to be our critical value. So we have to have enough of a difference to be in that 5% of the tails to reject the null hypothesis that there's no difference. T is the difference minus the expected difference divided by our measure of variance, which is the standard error of the difference. See Muse back. That's why I noticed it was gone before. Also, this hat should end here. That hat shouldn't be there. Okay? Done, copiers? Thank you. The standard error of the difference is that standard deviation divided by the square root of n. That's our old friend. We've done this one before. Again, larger sample sizes results in a smaller standard error. Less than 1's a pretty small standard error. Calculate our t-score. T equals minus 5. I already know that's statistically significant. That's really big. We were expecting 2 something, and it's 5. So we're going to reject the null hypothesis. It is very unlikely that we would have observed a change that much if in the population there was no effect of these trainings. Way out here. It's a very, very small probability that we have gotten this. The average knowledge scores for the 20 parents in our sample were statistically significantly greater. after completing a web-based intervention program than before the program. Anybody here have a campus job or work for the university? This is why you have to do slips, trips, and falls training online. There's like what, 10 modules you have to do online? There's way too many. You know why? Because they work. If you do them correctly. If you do them incorrectly like I do and you open up 10 different tabs for 10 different trainings and you just let them all talk over each other and take the quiz at the end because you're not an idiot and that water makes it more likely that you would slip, trip, or fall. Pro tip, you can do that. So, yep. These findings indicate that program can be an effective intervention for improving parents' knowledge of children's mental health problems and boost their confidence in handling such issues. The study finds lends support to the growing literature on the utility of offering web-based programs to improve the health of the general population. So things like this, why I teach half this class online, because you can learn online. Yes. There's 3 different ways in which you can compare 2 groups. One, if they're equal sample size, one if they're different sample size, or one if they're the same sample, just at different times. Okay. I want to show you one more thing in the last, what do I got, 15 minutes or so? So, no. So this was, our dependent variable was some sort of number where the mean made sense. So the time in seconds, that's something you count. The number of jumps, again, something you count. Your score on an exam, again, something that you count. So when we've been doing these are difference of means tests, right? Difference of independent means. There are some independent variables where the mean itself doesn't make any sense. And so there is something very similar to what we did for dummy variables. So if you have a dummy variable where your 2 outcomes are 0 and 1, the mean is the actual proportion of zeros and ones. So if you calculate the mean of between 2 groups of a dummy variable, you'll get a number. It'll be between 0 and 1, and all it will do is reflect the proportion of how those 2 groups responded to that question. Because it's a number, you can run it through a difference of means test. The problem is it's not actually a mean, it's a proportion. Because it's, again, just a percentage of how frequently you observe the 1. So you shouldn't do that. I forgot to print out the handout, but if you have a dependent variable that is a dummy variable, you can still do this procedure, but you have to use what's known as the difference of proportions test. The difference of proportions test takes into account that instead of it being a mu, it's actually a pi, because pi is for proportion. So it's just slightly different, but again, I just showed you 3 different things that are all essentially the same. So there's a handout there, and there's a video where I take like 15 minutes to walk you through that example. I didn't want to do that in class today because now that we're close that we can actually work on the paper, I want to demo some of the paper. Because the reason that I'm teaching this class to you all instead of just sending you to Stats 201 is because I want you to be able to use this stuff and write about it. So let's go to the paper section. So you now have the skills to start your class paper. If you can do a difference of means test, if it's appropriate to your data, you can start working on it. My strongest suggestion is that you use a website called Survey Documentation and Analysis. This has been around forever, and the great thing about it is in its data archive, it has two really big surveys. Oh, I'm in it. Okay. The two surveys that I suggest you use are either the General Social Survey. The General Social Survey is great because it asks the strangest questions about all sorts of things in your life. Like, raise your hand if you know anybody that's been murdered. Nobody? Just me? Okay, two of us. That's a question in there. We could use that as an independent variable. How might my personal experience with crime influence my opinions towards the death penalty, for example? I don't know. I think when Jimmy's stepdad took that hammer to his skull and bashed it in and then set him on fire, I think he's okay in dying. I'm good with that. I support the death penalty for Jimmy. Some of you are going, wow, you got real dark real quick. It's in the data, right? These are things that you can experiment with and test and see if that actually happens to other people other than me. The other study is the American National Election Study. This is the one that the political science folks use. So there's lots of questions in there about opinions towards government and society and what we should do. It's also great for like actual candidates in an election. A colleague of mine in grad school wanted to know why people didn't like Hillary Clinton. And this was back in like the early 2000s when she was just a senator. Like, why don't people like her? Well, the American National Election Study, not that one, this one, has a type of variable. So this is what you get when you sort of look at them. You have two options to find variables. One, you can use the search button, or over here, these are actually like collapsing directories. So you can sort of just click around and look at different variables if you want. Okay. But I want to look for Hillary. I want to spell Hillary correctly. All right. So there is let's take a look at this one. There is a variable in the data set. So people were asked a question about Hillary Clinton. Well, this sucks. See thermometer, question text, and nodes proceeding. I'm not going to look that up. Normally it has the actual question there. But this question is probably like, thinking of the following person, please rate them on a scale of 0 being cold and 100 being hot. Your feelings on blank, and then Hillary Clinton. So think of Hillary Clinton and score her between 0 and 100. Now, this is what they asked people to do. 2,679 people, 11% of the sample were like 0. 0. 115 kind souls gave her 1. She's not the devil, but she's close enough. 1. You'll notice that if you look at these scores, they tend to be on the 5s, so 5, 10, 15. We've given people an ability to give us an answer that is probably too precise. Right. Again, what's the difference between 91 and 92 degrees? It's hot outside. Like, do we need to know the exact precise measurement? Right. I don't know why they collapsed these into these categories. It might have been a coding issue, but 2,000 people gave them like her the top tier. I think it's because they wanted to preserve 98, 99 as the standard don't know or didn't respond. Also because they probably don't have 3-digit codes in the whatever instrument they were using to capture the responses. So 100 probably wouldn't have been an option. So anyways, So we can then calculate a mean score for opinion towards Hillary Clinton. And we can do that between two groups. So you can look at the difference between Democrats and Republicans, between men and women, between whites and non-whites, between Northerners and Southerners, or whatever you want to do. You can, as long as you define people into two groups, you can calculate the mean score for those two groups. Now, how you get the data out, there's a couple of options. One way is to download the data set as an Excel file. You all have access to Excel. It's part of the Office package that you do your email through. So when you sign in, you can click a thing over in the corner and actually download it to your computer. I show you how to take the data out of the SDA and put it into Excel. And for as much as I actually hate Excel because I can't get it to do what I want it to do, it does statistics. And if you were to take this class in the business school, you would be doing a lot with Excel. You can use it. The other thing that you can choose to do if you want to is the website actually has its own YouTube channel. And you can do analysis, because there's an analysis button, through the website. If you want to. That's up to you. One of the things that I don't like about the SDA website, or sorry, about the NES dataset, is that the variable names are awful. So you have to sort of keep notes as you're playing around what VCF0427 is. The GSS has great variable names. This is the example that I demo in the videos. Spanking. Do you strongly agree, disagree, or strongly disagree that it is sometimes necessary to discipline a child with a good, hard spanking? Okay. And so what I do in the video is I take this data, I download it. I got 5 more minutes, don't go anywhere. I download it into Excel, I recode it to make it either be agree or disagree. Because I think if you're willing to hit your children, it's either going to be a yes or no thing. Like you got that hand up and you're ready to smack them and it's either a yes or no. It's not a strongly agree like you're going to get this versus an agree like you're still going to get this, right? So you either think you should assault your children or you shouldn't. So I, in the video, recode this between 1 and 0. All right. You can recode it in the program as well and tell it how you want to do this. Again, you have to actually learn how to use the website. Your choice. I want my rows to be sex and my column to be spanking. What I did is I just ran a quick crosstab table to show me what is these, you know, the distribution between the two groups. And so I did gender. Because when I found out that when we had a kid, my wife and I had differing views on everything. Like absolutely everything. From what the kid wears to how hard we can abuse them, to expecting them to, like, you know, do the dishes, all sorts of things. Okay, I'm kind of making this up, but a little bit, right? So let's say there's a gender difference between men and women and how they view disciplining a child. The data is telling me, and it's got these really dark z-score things here, though don't trust it because it's just a computer. It appears to be that there is a difference. Not in the... Oh, that's wrong. Duh. This is why you need to pay attention when you're using this, because I forgot to click a button. So I'm going to turn the weights off, because don't use weights. You don't know what they are. And let's do a row percentage. There we go. Of the unweighted n. Weights are what people use when you do a random sample and it doesn't look right, like you're missing too many women. So we can weight different variables to make a more representative sample out of it. Okay, so for the males, 49 and 28, that's 77. 77% of the males agreed that you should spank your children, whereas let's call that 60% of females. So we have a gap, right, between 70-something and 60-something. Now we need to know, is that gap that we have observed in this sample of 26,000 people actually exist? Well, I can tell you right now, yes, it does, because there's 26,000 observations. That's a really big N. Think back to our equation for a standard error. When you take any number and divide it by 26,000, yeah, you're going to get a really high z-score. So if I'm smart, I might want to break this up a little bit, and I might want to look at the years that this question was asked. One of the features of these data files, it's great because there's a lot of questions, but the problem is that there's a ton of observations because they've taken every year and added them together. So there, you could have the situation where you find two questions that are asked in different years. And then when you go to do the crosstabs to look at the data, you're not going to get any observations because those two questions were not asked of the same people. So this question was asked in 1986. If I'm interested in time, and I want to say that, I don't know, corporal punishment of children has changed over time, I might want to sort of maybe just look at a year. I can filter out the observations for just 1 year. That is possible. You have this. It's free to use. There's a ton of information in these data sets. And one of the great things about this class is you can take the methods that you learn in this class and you can take them back to your majors. And you can write better papers in your majors. So if you're a public health major and you want to write a paper about smoking, guess what? There's data in here about smoking. If you're an Intel major and you want to write about, I don't know, whether we should torture people, there's questions in here about, hey, should we torture people? Right? You can make your other classes' papers much better by continuing this process into them. And you'll look like a better student. You'll be noticed because you won't just be copying what somebody else did. You'll be doing it yourself. You'll be closer to what I do when I write my papers. So these are websites that I really want you to work with and play with and impress me in your papers, but take it outside of this into your other classes because it's paper writing season.